Math 287, Cuesta College. I'm Joe Vasta, and we are going to cover 2.1, our first real lecture for differential equations, linear algebra, and we're actually covering linear algebra. Linear algebra starts off with matrices, so we'll do a definition of a matrix. A matrix is a table of entries, usually numbers. It is denoted by a capital letter such as A. The plural of matrix is matrices. So that's why this is called matrices. And we are going to look at an application and then get back to some math. So the application I'm going to use for a matrix, which is a table of entries, is from game theory. In game theory, people analyze games. It's a whole branch of math. Economists and business majors will usually take a game theory class. And what is happening with this game, it's like rock, scissors, paper, but we added more elements here. So we have paper covers rock, rock crushes scissors, rock crushes lizard, Spock vaporizes rock, scissors cut paper, lizard eats paper, paper disproves Spock, scissors decapitate lizard, Spock smashes scissors, lizard poisons Spock. So this set is right there. And what we like to do in math is take things that are kind of complicated like this and use a model and kind of get our hands on this without writing the pictures out or writing this all out. I mean, this looks pretty complicated. If you're a computer programmer, you'd like to put this into a program. How would you do that? You would use a matrix. So right here we have the payoff matrix for player 1, and that's what they'll do in game theory. And so here's player 1 right here, and player 2's up there. So when player 1 does a rock and player 2 does a rock, the payoff matrix means there's a tie there, so there is no payoff, and there's a 0 there. If player 1 throws paper and player 2 does a rock, well, somehow paper beats rock. I've never understood that, but player 1 wins, and the payoff matrix displays a 1, which means they get something. There's 1. Now, if player 1 does scissors and player 2 does rock, then there is a -1 because player 1, his scissors got crushed by the rock, and so player 1 lost, and that's why the -1 is there. So it looks like this matrix, which has 5 rows run this way, and 5 columns, it kind of displays the information for this game. So let's get back to the paper and me writing on the paper. So back to the definitions. We already went over this. A matrix is a table of numbers. Matrices. Rows of a matrix run horizontal. Columns run vertical. The entries of a matrix are called elements. If there are m rows and n columns, then the matrix is called an m by n matrix. We'll see some examples of this. The expression m by n is used to denote an m by n matrix, and there's like a little, looks like a multiplication sign. The expression m by n is called the size of a matrix. The numbers m and n themselves are called the dimensions of the matrix, though we'll try not to use that word because it's going to mean something a little different when we get to vector spaces. So let's take a look at some examples here. And our examples, if I can get this, this is really high tech, isn't it? They look like that. So here's some matrices here. And let's go over some of the vocabulary that we just went over. Rows run horizontal. So for this matrix, how many rows are there? There are 2 rows. columns run vertical, and so it looks like we have 1, 2, 3 columns. So how many elements are in this matrix? The elements are the entries. 1, 2, 3, 4, 5, 6. So there are 6 elements, which is essentially 2 times 3. The important part is figuring out the size of a matrix. The size of matrix A happens to be rows by columns. So this is going to be 2 by 3. 2 by 3 is the size. Now we're not going to write this all out with these other 2 matrices, but let's at least write the size. So the size of matrix B would be, well, there are 3 rows, 1, 2, 3, and 1 column, so the size is 3 by 1. And the size of matrix C, there's 1 row and 4 columns, so this is 1 by 4. And so that is what we have there. Let's continue with some definitions, and this comes right from the definition sheet that's on the website. We continue now, so we already covered dimensions. Those just those numbers, the rows and the columns. A 1 by n matrix is called a row vector. So we have this word vector, and we'll see this a lot. You may have seen this in other classes. An m by 1 matrix is called a column vector. The elements of a row vector or a column vector are called the components of the vector. Okay, so we have these special kind of matrices called row vectors and column vectors. Let's take a look at our example again here. This guy right here is a 3 by 1 matrix, so it's called a column vector. And this guy is a 1 by 4, so we call it a row vector. Oh, and by the way, just because I'm calling this one a row vector and this one a column vector, they're still matrices. Now this matrix here is not called a column vector or a row vector because it's not skinny like these guys. It's just a matrix. So these are special kinds of matrices. How many elements are in this matrix? There are 3 elements. So we can say 3 elements, or the new word that we've learned is 3 components. So you can say 3 components or 3 elements. Of course, we're not going to call these 6 elements components because this is not a vector here. Over here, this row vector has 4 components. Now there's some notation that I should tell you. I mean, this is matrix A, matrix B, matrix C, but when you have a column vector or a row vector, what we're going to do is we have another notation that we could use if we want, and that's by writing a little b, a boldface b. So because boldface b's are kind of hard to write with a pen, what we'll do is we'll put a line above it. And so this denotes vector b. And you've seen this in physics and maybe calculus 3 if you've taken that. And we could do the same thing with this. Here's matrix C, which is also written as a little c, a bold little c, which would take me a long time to bold that in, so we put a line above it. Now, if you're writing a paper, technical paper on the computer, you would just then bold the c, and you would not put a line over it. You would just use bold on there. So that is the deal with row vectors and column vectors. Let's continue with our definitions. There are a lot of definitions. This section is kind of low level in the sense that we're not doing really too much mathy stuff. Okay, let's take a look at this. The rows of an m by n matrix are sometimes called the row vectors of the matrix. The columns of an m by n matrix are sometimes called the column vectors of the matrix. So even though this matrix right here cannot be called a column vector or a row vector, we could still say what are, so let's ask the question. So we're kind of keeping this separated here. Let's see, do I have a ruler here? I have this guy right here. Just keep them separated like this. Okay, so they could ask in your homework, what are the row vectors of A? Well, how many row vectors? Well, there basically is how many rows are there, and we're going to write them as row vectors. So the first row I'll write like this: 2, -1, 3, and 4, 5, -2. So basically I'm just writing the two rows but as row vectors, putting brackets around them. So the column vectors of A, that would be the same deal. If they ask for the column vectors, I would just write these 3 columns with the brackets around all 3 of them. Okay, let's continue our definitions here. Definitions. Index form of a matrix A is the following representation. So we have the matrix here, and like this element here, I know this is very abstract for some of you, but this element right here is in the first row, second column. So that's why we call this element A sub 1, 2. And this is A sub 1n. Anything in the first row is going to start off with an A sub 1, and then it tells you which column it's in. And so lots of times, if you took a linear algebra class, higher level at a university, they would use this Aij in brackets there, which would then be used for a lot of proofs when they're proving things in linear algebra. Okay, so what do we have to know in terms of our example? Because that could have been a little overwhelming for some of you. Is this right here? Let's take a look at this matrix here. I think we're done looking at those guys. And I'm going to ask you what A21 is. So A21, we're looking up at this matrix. So tell me what that entry is. Okay, the entry, so when I say tell you what that entry is and then I kind of pause, you can pause the video and try to figure it out for yourself. I'm going to go ahead and tell you that it is 4. Now, why is it 4? Because it's in the second row, which is right here, first column. So that's what it is. Let me give you another problem. I'm going to pick an element from this matrix, like 3, and I'm going to have you go the other way. I'm going to ask, well, what is this? This is going to be A something. Well, there's only one instance of 3, which is good, and it's right there. So the subscript on that would be first row, third column. So that's A13. And that is the index notation for matrices. Let's go ahead and get to our next definition. So our next definition happens to be the transpose. The transpose of a matrix, of an n by n matrix, is formed by writing its columns as rows. The transpose of A is denoted A, and then it looks like an exponent, there's a T there, has size n by m, and that kind of makes sense. The sizes got switched around because you switched the rows and the columns. So let's go ahead and ask you on this example for matrix A, what is the transpose? It's really not that hard. So what you really want to do is let's write the columns as rows. So the first column says 2, 4. We're going to write that as the row. 2, 4. And the next column is -1, 5. So let's write that as -1, 5 along the second row. And then the third one is 3, -2. And so there's the transpose. The transpose note has size 3 rows and 2 columns, so this is 3 by 2. So that is the transpose of that matrix. Now we could ask for the transpose of these ones as well. I mean, the transpose of this matrix here would just be a row vector that says 3, 2, 1. But we just wanted to use this one here. Now, the formal definition, so you don't have to really worry about this. Formal definition, if you were taking linear algebra designed for math majors, would be, this is how they would define the transpose. They wouldn't say, or they might, but a lot of books wouldn't say this. It's formed by writing the columns as rows. They would say Aij transpose equals Aji. That's how they would define it. So, you know, if you're a math major, you get ready for, you know, maybe a future class where things get a little bit more technical. Okay, so that goes over transpose. Let's continue now. We can take this off completely and talk about equal matrices. Equal matrices have the same size and their corresponding elements are equal. Well, that's important to say. Equal matrices look identical. Okay? They look the same in every aspect. Elements are the same, the size is the same. The matrix negative A is obtained by multiplying each element of A by a negative 1. So you have to say that for some reason. An n by n matrix, so where the number of rows and columns are equal, that is called a square matrix. Now, why would that be called a square matrix? Well, because it looks like a square. None of those matrices right there happen to be square matrices. Square matrix has to have the same number of rows as columns. Let's take a look at some examples now. What we're going to be doing here is introducing you to some notation as well. Let this column vector be called D1, and then we have D2, which is that column vector. And then let D be this right here. So this is some notation right here, and you're thinking, am I multiplying them together? No, this right here is called a concatenation. You're just putting them together. This right here is notation. Okay, so what I want us to do in this example is to actually write out what D is. D happens to be, the matrix D, is we write this D1 as the first column, 4, 2, and we write D2 as the second column, negative 3, negative 1. And so this is what D happens to be, and this guy right here is a square matrix. The size of this matrix is 2 by 2. Okay, let's take a look at some more definitions. So on the definition sheet, we kind of take a little turn here. The next several definitions will be applying to square matrices only. So you have A is an n by n square matrix. The main diagonal is the diagonal containing the elements aii. Okay? Let's take a look at our example here. So aii would be a11 and a22 on this one, or should we really be saying d11 and d22? But in any case, that guy right there is the main diagonal. Great. Notice that this matrix here, well, none of these matrices have a main diagonal. So if I said, what is the main diagonal of A? It would be undefined because it is not a square matrix. Okay, our next definition. The trace of a square matrix, so this applies to square matrices, is the sum of the elements along the main diagonal. It is denoted TRA. or whatever matrix you're using. So in this case, TR, the trace of matrix D, happens to be the sum of the elements along the diagonal. So what is the sum of these guys right here? Well, if you add them up, you get 3. If we asked what is the trace of matrix A, the one from the last page, well, it's not a square matrix, so the sum of that, the trace of that would be undefined. Okay, let's go ahead and continue here. A matrix that has all 0 elements above its main diagonal is called lower triangular. A matrix that has all 0 elements below its main diagonal is called upper triangular. So we have lower triangular, upper triangular. Let's talk about those a little more here with these 3 examples. So what did we say? We said lower triangular is a matrix that has 0 elements above its main diagonal. This guy right here is lower triangular. Now, first, that may seem confusing, like lower triangular, because you see a triangle of zeros up above. And so that's kind of confusing for some people. So the way I look at this is all the information. Think of zeros as being not information, but the information is the 2, the 1, the 3, the 4, the 5, the 6. All the information is where? In the lower triangle of this matrix. So that's what makes this lower triangular. Yes, there has to be zeros up there. Now, a way of thinking about lower triangular when you're looking at 3 by 3 matrices is the following. So, I mean, maybe you want to look at it like this. A lower triangular matrix looks like this. There is something there, something there, something there. But there has to be zeros up there. And all the data is down in the lower triangle. And that one fits the mold. Okay, so that's what we have there. The formal definition, and some of you really don't want to see this, the formal definition. Formal definition of a lower triangular matrix would be this. A, I, J equals 0 whenever I is less than J. Okay, so for instance, this one right here is A1, 2. 1 is less than 2, and that's a 0 there. Now, a lot of you, now if you're an engineer, you know, maybe a computer science major, maybe you don't like these formal definitions. We're not going to have to know them to do our homework or the test. Just know lower triangular. To see this and see if it's lower triangular. Now, this guy right here is not lower triangular because those are not zeros there. In fact, the next one happens to be upper triangular. And the definition said a matrix that has all 0 elements below its main diagonal is called upper triangular. The data is all in the upper triangle. We can draw a similar picture for upper triangular. In fact, I'm going to go ahead and do that. Just to waste some time, I guess, doing that. So upper triangular looks like this. And this is for 3 by 3. So these triangular definitions hold for any square matrix. So we could be 5 by 5 and talking about this as well. That's an upper triangular matrix. I'm not going to do the formal definition with that. Some of you could probably already guess what that is. So this upper triangular matrix here is not a lower triangular matrix because, and you know, so these are what they are. G is an interesting example because it has 3 zeros there and 3 zeros there. So this is both upper and lower triangular. So that's pretty unique. In fact, that comes up a lot in linear algebra. So let's take a look at what the definition there. A matrix that is both lower and upper triangular is called diagonal. So this is called the diagonal matrix. Why don't we write that down? This is so it has to be both lower and upper, so these guys are not diagonal matrices. And it has notation. It is denoted by diag, and then it looks like that. So really, we can write matrix G as diag, and then we just pick up the data. The only data in this matrix that is important is the data that is along the diagonal. So we have 2, 4, 6. And so we can write it like that. That's the notation. This is probably invented by a lazy person, so they wouldn't have to write all this. But if you're working with 20 by 20 matrices and you have a lot of diagonal matrices, you're going to really like this shorthand. And if you want to do the purple for a 3 by 3 diagonal matrix, it looks like this. Where the little number thing that I draw could be any number. It could even include the number 0. So that's a 3 by 3 diagonal matrix. Okay, so that takes care of triangular matrices and diagonal matrices. This is all for square matrices. Let's go ahead and take a look at our next two definitions. Next two definitions are this right here. A matrix A is symmetric if A transpose equals A. So that's something kind of weird to say, but I mean, this is for square matrices. A square matrix A is skew-symmetric if A transpose equals negative A. Sometimes they say anti-symmetric in other books. They'll say anti-symmetric, but not in this book. So let's take a look at some examples, and we are going to ask, is the square matrix symmetric, skew-symmetric, or neither? And that's what we're going to be looking at. In your homework, the first section or two of homework in linear algebra, they give some weird problems where they ask you to write a symmetric matrix that's 4 by 4 that has some properties. So it's kind of a weird, I'm not saying all the examples are like that, but the ones near the end are kind of weird because there's not a unique answer. It's what you write. So let's go ahead and see what happens. And remember these definitions, A transpose equals A or A transpose equals negative A is going to give you the magic here. So symmetric, skew-symmetric, or neither. Let's go ahead and try that out. We still have another definition, but there were a lot of definitions in this section. Okay, let's take a look at matrix L. What could we do here? Well, in the definitions, you have to find out the transpose. Now, as you do more of these, you won't have to write this all out because we'll show you little patterns that you can look at. But the transpose of this matrix here is I'm going to write the columns as rows. So the first column is 1, 2, negative 3. And then the next column is negative 2, 1, 4. And then the last column is 3, negative 4, 1. Does L transpose equal L? Are they identical? And no, because look, this is a negative 2 right here, and that's a 2 there, so those are not equal. So it's not symmetric. Does L transpose equal negative L? Well, negative L, so we kind of define that. That's where you put negatives in front of each of these. So, of course, this is going to be a positive 3, a negative 2, etc. Are those the same? No, because there would be a negative 1 up there for negative L, but there would be a positive 1 there. So those are not the same. So it's not skew-symmetric, which means this one is neither. let's do this one right here. I'm going to go ahead and write out M transpose, which happens to be, first column is going to be the first row, so 0 to -3. Second column is -2, 0, 4. Third column is 3, -4, 0. Now, does M transpose equal M? And the answer is no. You can see there's a 2 here and a -2 there. So does M transpose equal -M? Well, -M, you would end up putting negatives everywhere. The zeros are going to stay 0, so this would be a +2, a -3, which you have there. -2, +4, +3, -4. So it does look like this is true. This is true. So this one happens to be skew-symmetric. Now, what's the quick way of checking for skew-symmetric? Well, for a square matrix to be that, you have to have absolutely zeros along the main diagonal. Because if you have anything else, or just one non-zero thing, then when you go to, say, -L, you're going to not have matrix transpose equals negative matrix. So it will have zeros along the main diagonal, and then look at this. The main diagonal is kind of acting as a mirror, sort of the evil mirror. So here's 2, here's its evil twin, -2, or its opposite. So when you're looking at reflections across the main diagonal, you have opposites on every other, all the other non-main diagonal entries. And so that's what makes this skew-symmetric. Of course, you can always go back to the definition, which says M transpose equals -M. Now, for this last one, we have N transpose. And as I'm writing this down, let's see, first column is 5, 2, 5. Second column is 2, 8, -1. Third column is 5, -1, 7. And that looks exactly like the matrix we have above. So N transpose equals N, which is true. N transpose does not equal -N, so this one is symmetric. Now with symmetric matrices, it doesn't matter what the main diagonal is. It doesn't have to be all zeros, but it acts as a mirror, and those have to be identical everywhere else. So -1, -1, 5, 5, 2, 2, and the main diagonal could be whatever. The skew-symmetric, the main diagonal would have to be zeros, and then the images would have to be opposites on all the other entries. So that's the kind of quick way of looking at a square matrix and seeing if it's symmetric or skew-symmetric or neither, but you can always go back to the definition. So this has been probably for a lot of you, this has been kind of boring. It's all been definitions. There has not been any theorems. There is actually one more definition that I should show you here, and that is the definition of a matrix function. We're going to come back to this idea of symmetry. But a matrix function is a matrix whose elements are functions of a single real variable, and you can call that variable t. And need to get a piece of paper out here for this. I just banged into the tripod. Oh, we're doing good. Okay, so we'll come back. So here's a matrix function. The matrix function looks like, maybe A of t equals, how about t squared sine t 7 square root of t 1 over t minus 2, and then the ln of t. So this is a 2 by 3 matrix function, and you could actually plug values in and evaluate this function. So like if t equals 7, I don't know why I picked 7, I saw the 7 there, then there's an output, and the output is not just a number, it is a 2 by 3 matrix. You could do calculus on these, take derivatives and integrate and all that other stuff. I did not assign any problems like that in here, but we will see matrix functions in this class, especially when we do differential equations. Okay, so getting back to, we have all these definitions, and it's pretty pointless, it almost seems, for a lot of you, but it's actually very useful. On the PowerPoint, we showed the rock, paper, scissors, lizard, Spock. And here is a 5x5 matrix. Let's go ahead and we'll go like this here. Okay, what do you notice about that 5x5 matrix? That 5x5 matrix is very special. Why would it be special? Because it is skew-symmetric. And so maybe that has something to do with fair games. There are games that you can design that are not fair games. This rock, paper, scissors, lizard, Spock is a fair game, and perhaps if you have a skew-symmetric matrix, then for the payoff matrix for player, this should say player 1 here. If you have a skew-symmetric matrix, then the game is fair. So that's probably a theorem from game theory. But it kind of took the skew-symmetric. I mean, now there is reason to be concerned or to be interested in these, because it means that you're looking at a fair game. And you can see, look, here's a 1 here, and there's a -1. Here's a -1 here, and there's a 1. There's 0 along the main diagonal. So it totally, and in game theory, you can have payoff matrices that have other numbers besides 0s, 1s, and -1s. And you can check to see when you're analyzing games if you do have a skew-symmetric payoff matrix for one of the players. Well, this completes 2.1. And keep up with your homework. There should be a PDF of all the stuff that I write out right next to the video. I'm not going to, when we have the definitions that look like this, I'm not going to go ahead and recreate these in the PDF, because you have a 20-page definitions and theorem sheet that is on the main website. So I'm only making the font bigger on these guys right here, so we can see them in the video and I can point to them. Well, do your homework and have a good day, and I'll see you in the next video.